From the dawn of humanity, we have gazed upon the starlit sky, our minds grappling with profound questions about our place in the vast cosmic expanse. How did it all begin? What are the fundamental laws governing the universe's evolution? These questions have fueled countless myths and scientific inquiries, driving us to unravel the mysteries of our cosmic origins. Over centuries, we have pieced together a remarkable narrative of the universe's history, from the fiery chaos of the Big Bang to the intricate tapestry of galaxies, stars, and planets that we observe today. Yet, for all our progress, the very beginning of the universe, the first fleeting fractions of a second after the Big Bang, remained shrouded in enigma. Our standard model of cosmology, while remarkably successful in explaining a wide range of observations, could only take us so far back in time. The Big Bang Theory left us with tantalizing clues about the universe's infancy, but the details of those earliest moments seemed frustratingly out of reach. Then, in 2014, a team of scientists working at the South Pole made an announcement that sent shockwaves through the world of physics and cosmology. To comprehend the significance of the Bicep2 findings, we must first delve into the concept of gravitational waves and their connection to the early universe. According to Einstein's theory of general relativity, gravity is not a force in the classical sense, but rather a curvature of spacetime caused by the presence of mass and energy. Just as a bowling ball creates a dip in a stretched rubber sheet, massive objects warp the fabric of spacetime around them. Gravitational waves are disturbances in this cosmic fabric, ripples that propagate at the speed of light. These waves are generated by the acceleration of massive objects, much like ripples on a pond are created by a dropped pebble. However, unlike water waves, gravitational waves are incredibly weak and notoriously difficult to detect. Only the most cataclysmic events in the universe, such as the collision of black holes or the explosive birth of the cosmos, can generate gravitational waves strong enough to be observed. The Big Bang, the event that marked the beginning of our universe, was the ultimate cosmic cataclysm. In the first infinitesimal fraction of a second after the Big Bang, the universe underwent a period of exponential expansion known as cosmic inflation. During this epoch, space itself expanded at an unimaginable rate, stretching the universe from a minuscule speck to an enormous volume. The announcement of the Bicep2 results sent a wave of excitement through the scientific community. The detection of primordial gravitational waves, if confirmed, would provide the most direct evidence yet for the theory of cosmic inflation. It would be a major triumph for our understanding of the universe's earliest moments and would open up new avenues of research into the fundamental laws of physics.
Having dedicated decades of my life to developing and refining the theory of inflation, seeing it potentially confirmed by observational data was an incredibly emotional moment.
A video capturing the moment when Linde hears the news from one of the Bicep2 team members went viral, showcasing the raw passion and wonder that drives scientific discovery.
However, the initial euphoria was soon tempered by caution. As with any groundbreaking scientific discovery, the Bicep2 findings required careful scrutiny and independent verification. The signal detected by the telescope was extremely faint, and there was a possibility that it could be contaminated by other sources, such as dust within our own galaxy. As subsequent analyses of the Bicep2 data were conducted, it became increasingly clear that the situation was more complex than initially thought. The faint signal attributed to primordial gravitational waves could also be explained by the presence of interstellar dust within the Milky Way.
This dust emits polarized light, which can mimic the signal of gravitational waves, making it challenging to disentangle the two. Further observations from other telescopes, including the Planck Space Observatory, added to the growing uncertainty.
Planck's measurements of the cosmic microwave background radiation, another relic of the Big Bang, suggested that the Bicep2 signal could be entirely accounted for by dust. While the Bicep2 team had taken great care to account for dust contamination, the Planck data indicated that the dust was more prevalent and complex than previously estimated.
The realization that cosmic dust might be masking the signal of primordial gravitational waves was a setback for the Bicep2 team and for the field of cosmology as a whole. However, it is important to remember that science is an iterative process, and setbacks are an inherent part of the journey toward understanding.
While the Bicep2 saga highlights the challenges inherent in probing the universe's deepest secrets, it also underscores the relentless spirit of scientific inquiry. The quest to understand our cosmic origins is far from over, and new telescopes and observational techniques are constantly being developed.
The search for primordial gravitational waves continues, with experiments like Bicep3 and the Simons Observatory pushing the boundaries of sensitivity and precision. These next-generation observatories will provide even more detailed maps of the cosmic microwave background radiation, allowing scientists to better distinguish between the faint whispers of the Big Bang and the foreground noise of our own galaxy.
Despite the challenges and uncertainties, the allure of the unknown continues to beckon us forward. The universe holds countless mysteries yet to be unraveled, and each new discovery brings us one step closer to comprehending our place in the grand cosmic scheme.